So number 6 then from the 2010 Higher Maths paper 2. What have we got? Tangents to a curve and area under a curve. Now the first part says, show that the equation of the tangent to this curve at the point where x equals 9 is this. So rather than it just saying find the equation of the tangent, in which case you just go through the routine, it just says show. So that leaves a bit of ambiguity there. Which way will you do it? Will you just ignore the fact that you've got the result and just go ahead and find it as normal? Or, equally valid because of the wording, just take that result and show that it does in fact work as a tangent. So there's 2 ways we could do this one. I'll take the standard approach first. Just what you would normally do if it said find the equation of a tangent to a curve. Right, here's the equation of the curve. There's the coordinate equation expressed in terms of y. If I want the gradient to every point in that curve, then you use the derived equation, the derivative. Notice you've got a function of a function. Doing the outer function first, which is power a half. That'll be a half of whatever is inside it. Take 1 off the power's negative a half. Have a peek inside. What's the inner function? 2x minus 9. What's its derivative? Don't forget to multiply by that. It's 2. So that means the derivative of this is going to be 2 times the half disappears. It's just this. The derivative is going to be, I think I'll write it out. Negative means 1 over, and a half is the square root of 2x minus 9. There's the gradient. I'll just go straight in with gradient now. Of course, you can just leave it in the form of 2x minus 9 to the power negative a half and use it in your calculations. I just prefer to put things back into this form of roots and denominators if I want to use them in equations or evaluations. So next thing would be this then. Right, define the equation of the tangent. That's a line, so it's going to be y minus b equals mx minus a. And to get the equation for this line, I need 2 things. I need the gradient, I'll get it from here, and I need the coordinates. I've only got the x so far, so I need the y coordinate, I'll get it from here. So I need those 2 things. So, gradient. When x equals 9, that means the gradient will be, I've just got it straight in this form, 1 over the square root of 2 times 9 minus 9. That's 1 over the square root of 9, so that's 1/3. What's the y coordinate? Well, that power a half means the square root again, and it's the same thing, isn't it? It's 2 times 9 take away 9, so it's the square root of 9, which is 3. Maybe it would be neater putting those to the side so I could have followed down directly under that. So the equation of my tangent will be y minus the y coordinate equals the gradient times x minus the x coordinate. Now you are used to just leaving it like that. Whenever it asks this type of question, think that's all that's necessary, but not in this case, because it says show it's equal to this. So I'll need to follow that one through. Now, normally you take that across and multiply. There's no need here because that 3 will divide into that 9, and I can see I want to leave the 3 as a denominator in front of the x anyway. So I'll just say y minus 3 and just multiply out the brackets. It's 1/3 of x, and 1/3 of 9 is 3, which means that y equals 1/3 of x. You'd have to put it into this final neat form rather than that form to get the final mark for this question. Now, an alternative to part A then would be just to verify that that in fact is a tangent to this, in that it meets it at only 1 point. So that I have this, and I have y equals 1/3 x. If I call that equation 1 and that equation 2, then I can say, well, if I substitute those together, so if I substitute, I'll say 1 in 2, quite often you don't bother putting that down, you just think equate the y's. I would have 2x minus 9 to the power a half equals 1/3 of x. And then you think, oh, I'm not used to seeing this sort of thing. It's quite simple, just like you don't like fractions, so you might get rid of them first. Here's a square root. How do you get rid of a square root? Square both sides. Squaring this side just re-establishes the 2x minus 9. Squaring that side, don't forget to square both parts. A square of 1/3 is a 9th, and a square of x is x squared. You know, I'm thinking I should have equated that the other way around. No problem, I'll just write it backwards. 1/9 of x squared minus the 2x plus the 9 equals 0 would be the quadratic. Now again, you've got two roots. Will I factorise it and show that I've got equal roots, or will I work out the discriminant? I'm just going to factorise it. Well, in that case, I don't like that 9th. I'll just multiply everything by 9. So I've got x squared minus 18x 9 times it plus 81 9 times it. And then that readily factorises. 9 9s are 81 and 9 and 9 is 18. So that's x minus 9 squared. Now, as far as this question's concerned, this part's concerned, I don't need to go any further. All I want to do is verify that that line is a tangent. I don't need to verify the point of tangency. I just need to verify it's a tangent by showing it only hits it once. And here we are. So at this point I can stop and say from here I've got equal roots. Equal roots, which means line 2 is a tangent. I think it's enough just to say line is a tangent, but I'll say it is a tangent to curve, I can't even read that, to curve 1. They tend to prefer you to say things like equal roots. I used to just say only one solution or only one point of intersection, which are equally valid for the mark. But you really just stick with equal roots, so it's a tangent. Of course, if you didn't want to do the factorisation, you could have worked out the discriminant. And then you would have got a discriminant of 0. And then you'd have said after that discriminant of 0, equal roots, line is a tangent. But that's not the only way to verify that that line is a tangent. There's one more way. It's a wee bit more dodgy because you have to be careful to put in more information. And that's to say that line will be a tangent if the gradients are the same at that point. Notice, I said at that point, not just at that x. I'll mention that in a minute. So that would mean work out the gradients of the two lines where x is 9, or show that they're the same rather when x is 9, or just put x is 9 into it and show they're the same. That would do as well, wouldn't it? So first one, we've already done this one. dy by dx, the gradient of the first one, I'll call that m1, is, we had at the end of that, 2x minus 9 to the power negative a half. Remember, because it was a half times it and then times 2. The gradient of 2, straight away by inspection because it's a line, equals a third. Now, I don't actually see what's wrong if it's just a verification of putting the value 9 in for x and showing that that also comes to a third. However, looking at the marking scheme, for this particular method, if MD decided to do it, they seem to want you to establish that it happens at x equals 9. So, putting in that equation the way it was before, that means 1 over the square root of 2x minus 9 is equal to 1 upon 3. Well, that then means those denominators are equal, or cross-multiplying if you like. So the square root of 2x minus 9 is equal to 3, squaring both sides. 2x minus 9 is 9. 2x equals 18, so x does in fact equal 9. But that's not enough in this case. All that that says is the line and the curve have the same gradient, which is a third, where x is 9. But that doesn't necessarily mean that they're tangents. You can have a curve and you can have a line where at some value x equals 9, on the curve the gradient is a third, and on the line, obviously it's the same all the way through, the gradient is a third, but they're not tangents. You'd also have to show that they've got the same y coordinates, so they touch at the same point. So I'd have to go on and say for the first one, so for the curve, for 1, when x equals 9, y equals 2 times 9 minus 9 to the power a half. So that's 9 to the power a half, which is 3. For the line, y equals a third of 9, which equals 3. And then you can say, on the curve, the point is 9, 3. On the line, the point is 9, 3. And then you can say, same gradient at same point, which means, as before, the line, I'll just put the line as a tangent. Why not, to the curve. So there's a third option. Probably an option you shouldn't go for, because you'd probably forget this last part of it. So, part B. Diagram 1 shows, oh, it only refers to this diagram now in part B, which means you were doing part A blind. You should have been ignoring that diagram in effect. So anything you did in part A shouldn't have had reference to that diagram. All the information was there anyway, the two equations and the fact that it's at x equals 9. But one thing you shouldn't have used in part A from this diagram is the fact that that line goes through the origin. When you were determining the equation of the tangent to that curve, you found the derivative, you got the gradient, you put 9 into that. When it comes to the y minus b business, it was that point 9,3 you had to put into it, because that's the only point you knew. You couldn't put in the origin, because that was by glancing at the result here. You'd have lost the mark if you did that. Anyway, what's this? Part B, simply what are the coordinates of A? Well, A is a point in the curve, so it's got to satisfy the equation, which means that to find one, I need to know another. And if it's on the x-axis, I know that y is 0. So I've just got to solve the equation equal to 0. So I'll just put it down that way. At A, I know that y is 0. That means that 2x minus 9 to the power of half equals 0. Now it's only one mark, so I don't need to go through the whole business of squaring both sides. I could probably just jump in straight away with saying 2x must equal 9, so x equals either 9 upon 2 or 4.5 or 4.5. I don't know which one I'll put down. I'll put 4.5. So that A is the point, 4.5, 0. So what's this last part? Calculate the shaded area shown in this second diagram, which is just the first diagram with the shaded part shaded in. 7 marks here. Now, well, there's 2 ways you could do that. Notice you can't just do it in one go though, because even though that's just one block of area, there might just be one equation that gives the top of that area. Those would be the y coordinates of the tops of each of these little bars. There's 2 different equations for the bottom of that area. So you'd have to split it into 2 parts. You can either do it just simplistically, just by concentrating on the shaded part, just focusing on that and thinking, well, I'll just split it here. So that the area would look like, split it as far as that, that's a little right angle triangle, and then continue for this bit by having a proper area between 2 curves, because now there is just the one equation for the top and one for the bottom. You could do it that way, or it might be easier just to think of it as a big triangle with this part cut out of it, with this part missing, the part here missing from it. That would then leave you with this part here. Obviously I'm going to do them both, although that's a better way, because that's going to be a simpler integration, and I already know the top point of this triangle, so I can work out its area. So this would be the preferred one to do, although both will give you the answer. This should be easier though. So I'll say area of the triangle, that would do just to put a wee triangle sign in, is a half base times height. I don't need to justify any of that because I already worked out the coordinate of that point to be the point 9,3. I could have put it into the diagram, I suppose. So that's a half of 9 times 3, so that's going to be 27 upon 2 square units. Then I could just indicate it on a diagram on my page, or just use the words. Area under curve would be the integral from, that was 4.5, wasn't it? I'll put it back as 9 upon 2. From 9 upon 2 to 9 of simply that equation, 2x minus 9 to the power of half dx. Integrating, lifting up the power, so that's going to go to 2x minus 9 to the power 3 upon 2, then divide by 3 upon 2, but I always think better than that, just multiply by the reciprocal, which is 2/3. But don't forget to also divide by the derivative of the inner function. You've got a function of a function. If you were differentiating, which you did do, you multiplied by the derivative of the inner function. In integration you do the opposite, so that'll be divide by that 2, so I'll put that down there. That can join the denominator. So this is what has to be evaluated from 9 upon 2 to 9. Now I could use another line just to tidy that up, but obviously it's just going to be a third. Another thing you can do is, that third's going to appear in both evaluations. You could take it out of it. but you probably leave it in, so I might as well just leave it as well. And this is the tedious bit now. It's just a case of replace the x's with these numbers first, so I'll just rewrite that, I'll just leave that third in. So it's a third of 2 times, putting 9 in, minus 9 to the power 3 upon 2, minus a third of, this time it's going to be 2 times 9 upon 2, minus 9 to the power 3 upon 2 for the area. Don't actually need brackets around each part since they're only a single term. And those brackets are put down don't match anyway. Notice how you could just have kept the third out of that though. So that's going to be, in this case, that's 9 to the power. Now after this I suppose you're just going to say, oh, just press the buttons on the calculator, which fair enough is probably what you would do. But I'm not going to do that, I'm just going to work it out. In the example it'll be safer to do that. I'm just going to work it out. Because that's just going to be 2 9s, take away 1 9 is 9. Square root of 9 is 3. 3 to the power 3 is 27, but I'm dividing by 3, so that's going to go to a 9. So that part's 9. This part, 2 times 9 upon 2 is 9. 9 take away 9 is nothing, so it just becomes 0. So this then becomes, the area under this is going to be 9 units squared. Not a lot of working really. And then finally, the area that they're actually looking for, so I'll actually specify, the shaded area will be the triangle, which is, you could either leave it like that and make them both halves, or put that to a mixed number, whatever takes it. You could even put it as a decimal, whichever takes your fancy. I think I'll put that back to a mixed number. That's 13.5. That's 13.5 minus the 9, which is 4.5 square units. Now, what would have happened if it was just that shaded area that grabbed your attention, so you decided to do it this way, by splitting it into a triangle and the sliver of an area between 2 curves? Well, you'd have had to get the triangle first, but it wouldn't have been as simple, because for the triangle, I'd have to say something like, for the small triangle, it would be a half base times height, but I'll have to work out the height here, using that equation. So I'll say small triangle, I'll just put in the information. The base is definitely 9 upon 2. The height's going to be given by putting that into the formula, which is 1/3 of 9 upon 2. So that means the height's going to be, 3 into 9 goes 3, so that means the height's going to be 3 upon 2. Then I can get the area of that triangle as a half times 9 upon 2 times 3 upon 2, which is a horrible looking 27 upon 8 square units. It's looking worse already. Now for the area of that sliver, which is an area between the curves, we'll just put this down, will be the integral from, now it's still the same, it is still from 9 upon 2 to 9, but it's going to be worse, because I have to make sure I do top take away bottom. The top is a third of x, the bottom is the 2x minus 9 to the power of half dx. Where you go. Looking worse already. So integrating that would be up to power 2, divide by power 2. I'll just leave it this way just now. This one, function of a function, deal with the outer one first. Add 1 to the power, 3 upon 2, divide by that, but rather than writing over 3 upon 2, which creates a complicated fraction, just multiply by the reciprocal. So minus 2 upon 3, but don't forget to divide by the inner derivative, so that's times a 2, to be evaluated from 9 upon 2 to 9. I will tidy it up this time, because that's a sixth. You've got a sixth, looking terrible isn't it? A sixth, but that's only a third, of 2x minus 9 to the power 3 upon 2 to be evaluated. Now I've got to go through the rest of the palaver, which is one line to do the substitution, and then another line, fair enough, just for the answer, press the buttons. One line for the substitution, again you could take that third out and just leave a half here. I'll just keep it in. 1/6 of, first of all it's going to be 9 squared, minus 1/3 of 2 times 9 minus 9 to the power 3 upon 2, minus 1/6 of, this time it's 9 upon 2 squared, minus 1/3 of 2 times 9 upon 2 take away 9 to the power 3 upon 2. I'm not going to press buttons. So that's 81 over 6, they both divide by 3, that's 27 upon 2. That's just a single 9. Square root 3 cubic 27, but divide by 3, 9, minus 9 for that part. Minus, it's even worse, that's the same as this one, that's 27 upon 2, but there's a 4 underneath it, so it's 27 upon 8. But luckily this part here, 2 times that's 9, 9 take away 9 is nothing, so that's minus nothing. Running out of space here, but I think instead of I think I'll just go back to mixed numbers. Mixed numbers are more appropriate for adding and subtracting. So that means this part here is 13.5. Take away 9 and take away this part here, 8 into that is 3 and 3/8. So 13 take away 3 is 10, take away 9 is 1, so it just comes to 1. 1/2 take away 3/8, 4/8 take away 3/8 is 1/8, so that's 1 and 1/8 units squared. Far worse. Not finished yet, I've got to add them together now. So now, shaded area. Now I'll just put that to a mixed number. So for this one, that's going to be, it was the same as that, wasn't it? That's the 3 and 3/8. 3 and 3/8 plus the sliver, 1 and 1/8, is 4 and 4/8, which is 4.5 square units. A much worse way of arriving at the correct answer. Still a valid way, but a regrettable way if you set off in that path when you came across all these numbers. So much simpler by thinking of the big one, take away a missing part.